Hey audience, some time ago I had a hankering to build a radio. I never actually got around to building one, but I did end up with what I think is a neat piece of homemade lab equipment that I think everyone would have some use in having around. I have some bread slicer style variable capacitors that I picked up at a ham fest a while ago that I wanted to use, but I had no idea what the range of capacitance was, or if they were linear, logarithmic, or something else. I also couldn't find any good references or calculators online. I've measured capacitors with an Arduino before, and it's simple enough. Just charge the capacitor through a resistor, wait until the voltage on the cap rises to 2/3-ish of the charging voltage, and the time it takes is the time constant of the RC circuit. Just divide by the resistor value and boom, easy. But these radio capacitors have a low end of near single-digit picofarads, and this method has some serious problems when measuring capacitors that small. One problem is that the capacitor charges really quickly. In order to make the time constant long enough to measure accurately, it needs to be charged through a really large resistor. That makes it take way too long to measure larger capacitors. And at this point, I'd already decided that I didn't just want to measure this one capacitor. I wanted to build a meter to have on hand for any capacitor. I could use multiple charging resistors on different pins, but that would be nice to avoid if possible. Large resistors also have higher voltage noise, which might make that measurement less precise. But let's be real here, we don't really care about any of that. The thing is, even with large resistors, more insidious problems start showing up. The input pins on the Arduino have their own parasitic capacitance that's on the order of roughly 30 picofarads. So when the capacitance you're trying to measure gets small enough that it gets close in value to this input capacitance, maybe below 100 picofarads or so, you start getting noticeable errors from measuring the input capacitance along with the capacitor under test. One solution found online came in the form of a fantastically simple setup that uses the input capacitance as a feature rather than a parasitic nuisance to work around. I've put some links in the description to some discussions of how it works. Here's the circuit. That's it. You just put the capacitor on two of the Arduino pins. No measurement resistors, no nothing. Looking through the code to see how it works, it actually uses two separate techniques to measure the capacitance and switches between them based on the size of the capacitor. Let's walk through them one at a time. For small capacitors, we turn one of the pins into an analog input. The ADC looks like a capacitor to ground. That's our parasitic input capacitance. The other pin we turn into a digital output and set it to output high. The structure we end up with looks kind of like a voltage divider, but with capacitors instead of resistors. And wouldn't you know it, the ADC measures right at the middle of it. I personally haven't seen voltage dividers made with capacitors used much outside of maybe Colpitts oscillators, so I think it's worth talking about it a bit. We can analyze a capacitor divider in a very similar way to a resistor divider. With a resistor divider, we start by saying the same amount of current is flowing through both resistors since they're in series. There won't be any current flowing through the capacitors in steady state, of course, but there was current flowing when they were charging. Some number of electrons get added to the bottom plate of the bottom capacitor, and the same number of electrons get displaced from the top plate. Remember, capacitors don't store charge, they store energy as the displacement of charge. The amount of charge added to one plate is always removed from the other, so the total charge in a capacitor is always zero. Anyway, those displaced electrons go to the bottom plate of the top capacitor, and that displaces the same number of electrons from the top, which return to the circuit. The actual cause and effect chain doesn't quite work like that, but it's a good enough model. So we can see that the amount of charge displacement is always the same in both capacitors, since the same amount of current ended up flowing through both while charging. Now we remember that capacitance is defined as the amount of charge displacement that you get per unit of voltage that you apply to a capacitor. Higher capacitance means you get more charge displacement for the same voltage. We can run that formula in reverse and apply it to this capacitor divider. We know both of these capacitors have the same charge displacement, we know the voltages over both of them from the ADC measurement, and we know the value of the input capacitance, so we can solve for the test capacitor. Just as an interesting side note, in a resistor voltage divider, the larger of the two resistors will have a larger voltage drop over it. In a capacitor voltage divider, that's reversed. The larger capacitor will have a smaller voltage drop over it because it takes less voltage to cause the same charge displacement in a larger capacitor. Something to keep in mind about the voltage divider method is that it works best when the capacitor that you're measuring is roughly the same size as the other. As you make the test capacitor larger and larger, the voltage at the test point changes less and less, which gives us poor resolution. If we measure a voltage close to VCC at the test point, That doesn't tell us much other than that the test capacitor was much larger than the input capacitance. That's just fine because that means we can safely switch back to the classic time to charge method. But how can we do that without any resistors attached? The answer is to use internal resistors already on the Arduino. We can set a pin as a digital input with an internal pull-up resistor so that it looks like we have a resistor to VCC connected to our test capacitor. We then change the other pin to be a digital output that's set to output low, and we have our classic RC circuit. You'll notice that we don't have an analog input to actually measure the voltage on the capacitor this time. We do, however, have a digital input so we can detect when the voltage rises above the threshold that represents a logical 1 by waiting for the input to transition from low to high. That's probably not going to be good enough for measurement, but we can at least know that we need to stop charging the capacitor. At that point, we turn the pulled-up digital input into an analog input and then read the voltage on the capacitor for a more precise measurement. Because we're not stopping the clock when the voltage reaches that 2/3 VCC sweet spot that lets us know that a single time constant has passed, computing the capacitance isn't as simple as just dividing by the resistance anymore. But since we know the function of voltage over time for a charging capacitor, we can still do it. We have the technology. There's no law that says you have to measure exactly one time constant. It's just a bit more convenient that way. This also means that for large capacitors that take a long time to charge, we don't actually have to wait that long. Waiting for a logical 1 will be fine for fast-charging capacitors, but after waiting for a certain long amount of time, we can just give up on waiting and measure the voltage early. Our new formula will still let us compute the capacitance, so we can measure large capacitors faster than with the traditional wait for one time constant method, by just not waiting for a whole time constant. Then there are just a few extra bits of code to make sure that the test capacitor is discharged between measurements, determine what type of measurement to make, and some display code. My display shows 4 digits worth of value on the display and lights up a scale LED to give you the units, either pico, nano, or microfarads. It's what I could throw together with what I had lying around, but I'm really happy with how this looks. I'll probably use the same display method when I build an inductance meter in the future. My code's up on GitHub, with a link in the description. Of all the DIY methods for measuring capacitors using an Arduino, this is simply the only one I would ever recommend. There are no external components, and it works over pretty much the full range of capacitors you would expect to see, nearly from 1 picofarad to 1 millifarad. And it has this really cool elegance to it by using parasitic features to our advantage instead of working around them. Would I do this if I was a product designer designing a capacitance meter? Probably not, specifically because of its use of parasitic capacitance and pull-up resistance for measurement. I couldn't find good references from Atmel about the input capacitance of the pins, so it might change from one Atmel part to another, or even from one batch of the same part to another. It might depend on temperature in a way that you don't expect, too. I might not translate well to PIC or TI microcontrollers because of differences in ADC design. The input capacitance was simply not intended to be used as a precision reference for measurement. The same goes for the pull-up resistor. There's a rough target that they'll try to meet, but for the job of pulling up a digital input, there are no precision requirements other than that it has to be somewhere in the ballpark of this value. So if I had to guarantee certain performance of a capacitance meter, I would do something else. But it's absolutely good enough for any hobbyist who wants to measure capacitors at home, so build this. It's great. Now that I have a capacitance meter for those mystery variable capacitors, it would be nice to have an inductance meter for some mystery hand-wound coils. But that has its own difficulties, again, especially around small values. So we'll see if I can't get one working as well as this one here does in a future video. I'll see you then.